Hello everyone, I'm Vaibhav and welcome to my final project presentation titled Loan Approval Classification. Have you ever wondered how banks decide whether or not to approve a loan for a given loan applicant? Well, they use machine learning and data science to make those decisions. And in this project, I have built a machine learning pipeline to predict loan approvals based on applicant data. I will walk you through the entire process, explaining each and every step and its significance. So let's get started by diving straight into the code. I began by creating a normalized database in third normal form to organize loan data efficiently. And this ensures that data is clean, avoids redundancy, specifically transitive redundancies that were present in this dataset. So, just for example, there are things like person's education, income, employee experience, home ownership, loan amount, intent. Like there are few columns in this dataset that are more transitive in nature. So as you can see, that person table stores applicant details like age, gender, education, like person specific details. The loan table contains loan specific attributes. The credit table contains uh, credit related attributes like credit history, amount, not amount, any previous defaults, any credit ID and the credit score of the person. And the loan status tracks things like loan approval status as well as what's the credit ID, what's the loan ID, and what's the status ID of that loan. And then, as you can see that after transforming this data set into third normal form, it is important to like write a join query to fetch that data from our data set into our pandas data frame. So that's what I've done in the next section of this uh, Jupyter book. I have some uh, data stored in my SQLite DB, and then I have written a join, uh, uh, a large join query to get that data from the database into pandas data frame right here to CSV. And basically, I have read the data using here with pandas. I have displayed the output of the first few rows, and then I have stored all the data into normalized data, load data.csv. And as you can see, the output has been successfully written. And again, since we have so many rows, like roughly around 45, 450,000, so so we can just afford to drop any row which has a null value. And then we move on to a little bit about whether or not we should stratify this data set. So here we have uh, basically plotted a bar chart of loan statuses. So as you can see, a lot of loans were rejected and very few were accepted. So it's a little bit of imbalance, which we can fix by stratifying this data set on loan status. So moving on, and here you can see that I haven't commented out the Y profiling code because the running Y profile over here causes issues in some other packages in the code below. So I have done the Y profile at the very end. And as you can see, here we have all the information about each and every column of this data set. So moving along to our next section, which was correlation matrix. So here we have plotted a correlation matrix of all the columns in this data set. There are a few columns which are highly correlated. We don't want that, right? That's a little bit of EDA for you. And here's where we're trying to decide how to stratify the data. And basically, we found that we have to stratify it on load status. And so that's what we have done here with stratify equal to Y uh, attribute here. And again, as you can see, the data set is now divided into a nice little 80-20 split. So moving along to the the training data, and this is the testing data right here. Loan labels and loan. As you can see, test or copy. That's the testing data set, and loan contains the training data. So moving along to pre-processing, and here we have doing some standard scalar as well as for and log transformation for numerical values and one hot encoding for categorical values. And here we are logging everything into DAGSUB and MLflow. So as you can see, we have load train.csv, load test.csv, which we have saved earlier, and we are doing some pre-processing on that data. And you can see this nice little pre-processing pipeline that's set up here. And then we try to create another pipeline which combines these two pipelines, which is pre-processing as well as logistic regression. Then we do a little bit of cross validation and apply the logistic regression model and then log the results into MLflow. And as you can see, this is the link generator for DAXA, and this is a best F1 score that we got with logistic regression and pre-processing. So here's a little bit of hyperparameter tuning that I'm doing, and here are the different regularization strengths. And after running this hyperparameter tuning, we found that this is the best hyperparameter 10.0. And then we are going to create a pipeline for pre-processing and for uh, basically running this data, be able to run four models on this data, right? So one of them is logistic regression, which classifier, random forest, and XGBoost, which stands for extreme gradient boosting. And as you can see, we are importing all the important libraries, and we are creating a pre-processing pipeline right here. And then we are running all these classifiers uh, on, on our data, and then there's this little uh, output over here where we get a lot of logs into DAGSA. So you can check out these logs in links and references section of this Jupyter book. I'm not going to go through each and every of them, but I can just mention that the XGB classifier gives us the best F1 score. This is a little bit suspect, so I haven't chosen that. And other classifiers like logistic regression and rich regression, they're not that impressive. So I went with the XGP classifier. That's what I've done here. Model, I'm saving model as new model. You may guess what this model. As you can see, this is a for loop, and the last uh, classifier was the XGB classifier. So XGBoost model basically gets saved in the model variables, and that's what we are going to dump into new model.joblib. And we are also dumping our pre-processing pipeline into a separate joblib. And here we are doing a little bit of feature engineering where we are going to create new features like debt to income ratio, credit utilization, income stability, loan to credit ratio, and then uh, run all of that through a pre-processing pipeline. And then basically, uh, here you can see for numerical, we have log transformer, standard scalar, and for categorical, we have one hot encoding, and then feed all that data into logistic regression and log all these results into MLflow. Slightly improved F1 score over here thanks to feature engineering. And then we are doing feature selection using correlation threshold and feature importance and variance threshold. So here's what we have done. Fetch the data from normalized dataset. And as you can see, it's a lot of code, but you can see that we are selecting important features from the random forest classifier and sorting them in descending order, and we're going to plot them right here. So these are the top 10 important features. As you can see, the most important feature is previous loan default on file. And this is the feature correlation matrix. We're going to drop all the features which are highly correlated, and we're going to log our results into MLflow again as usual. And then here we are doing PCA, which is principal component analysis, as we know that each data set will have a few features which will help us explain the maximum amount of variance in our data set. And there will be few features which don't explain a lot of variance in the data set. So we want to select those features which help us explain the most amount of variance. And that's what PCA analysis does. It helps us identify the principal components of that data set. And here's a little bit of scree plot. As you can see, there are a few principal components that you know uh, in, result in the cumulative explained variance ratio jumping from, let's say, from 3.5 to more than 5.5. And then second principal component causes this jump even further, right? Sorry, the first principal component causes jump from 0 to 3.5, second one causes from 3.5 to 5.5, and so on and so forth. So we want to retain at least six principal components, which explain like roughly 95% of the data, and these other two are not that significant. And then moving along to design and execution of a custom experiment, which is, or in this case, I've chosen a naive-based classifier. And again, same thing, but a little bit of difference that I have used a PCA reduced data set because naive-based doesn't give that good F1 score or accuracy for this data. But using the PCA reduced data set actually helps us to increase the F1 score for the naive-based. And here you can see that the classification report has been printed along with the confusion matrix. And the second custom experiment that I ran was the decision tree. And as you can see, I have fetched data from normalized loan database dataset, and I have logged all the results into tags up, as well as plotted the confusion as well as the classification report. And here, as we reach the end of our Jupyter book, I have plotted F1 scores of each and every model that we have received. This data is from the MLflow DAX of logs, and as you can see, the XGBoost gives us the best F1 score. That's why I have selected XGBoost for deployment. And I have profiled the data down below because of the dependent packages dependency issues, right? So now let's jump right into our code, the deployment of our code. So here you can see like there's a Streamlit app, and I have set up a few sliders for each and every variable that we have in our data set. So here we have percentage, we have a person center, we have whether the person is a bachelor, what's the education level of that person. We have the income, employment experience, home ownership, whether the person owns a home or not, or whether they are renting or have already mortgaged the loan amount, loan intent, interest rate, all these other variables. You can just change these variables and you can see the change reflecting here as well. So here, right now I have personal income as 12%. If I decrease it to 11 or increase it to 20%, it reflects here. When I click on the predict button, it gives me a prediction result, which is loan status denied. So I already have another Streamlit app running, which it's the same. It's the same app, but just a different uh, data, and I think that's gone now. So let me just pull up one of the data that I have in with me. So let's go to let's pick a data point that makes it more likely for a person to get a loan, right? So here you can see it's all zeros. Let's scroll up. Maybe we can find something. Yeah. So over here you can see that person's age is 22, female, and we'll try to input the data which is closest to this kind of person. So let's say this person's age is 23, it's a female, and master student. So education is uh, kind of preferred for a loan, I guess. Master student person has an income of 71,200, 72,000. Basically, we put income as, let's say, 77,000, I guess. And then employment experience as 0 years of experience. So employment experience not that much preferred. I'll just put 1 year experience there. Person does not own a home; they rent the home. So I'll select rent here as well. What's the loan amount? 35,000. I'll select a slightly higher loan amount. Let's say 37,000. Loan intent as personal. So we put it personal. Interest rate is 16%. We put something like 15.5, 15.28 is enough. And loan income percent income is 0.49. I'll put something like slightly higher, I guess 0.5 is enough for now. And credit history length should be like 3 years, so not that important for at least for this. And I'll just put true. Let's see what happens. And credit score is pretty bad, but let's say this person has 540, 550 as credit score, 551, or slightly higher, I guess, 560. And there are no loan defaults on file, right? For this person. So let me get this out of the way. Yeah, false. Let's see what this prediction provides us. And yeah, as expected, since the data is point is very close to this first person, the loan status is approved. So yeah, so that's all from my side for now. I have included all the links and references over here with tags of links and the link to my Streamlit app. And as you can see, I have created a droplet in DigitalOcean where I have deployed my fast API backend in this IP address. This is my Docker Hub container that I have deployed in the droplet. This is the dataset that I have used, and this is the front end of the application. And these are all the uh, DAGSUB logs that I have generated when I ran the Picture. So that's it from my side. And before I conclude, I would like to thank Professor Zia for his valuable insights in machine learning and his knowledge and his ability to teach all these concepts in such a clear manner has really helped me with this project. So thank you, Professor, for everything that you do. And thank you all for watching my project presentation and see you next time.